Have you ever wondered how data is stored safely on disk? Well, in today's video, I'll be explaining that. So, basically, this is a brief overview of the simple engine that I built from scratch myself in Python. This is basically a storage engine, and in there, I also use a B-tree to store data in memory and how to organize it. So this is an example. We use db.insert cat. Then what will happen under the hood is that a program will call for the root address, which is here, and on disk I reserved like 4096 bytes, which only stores the metadata, for example, whether it's a text, a number, a boolean, or a null pointer, and also the root address, which is the location on disk where the binary tree data actually starts from. So it will retrieve this from there and then begin to recursively go down the data structure to insert where this cat and q to be at, so that it can perfectly fit into that. Then when it's done, as soon as we want to store data on it, we would first of all lock the file to avoid concurrent reads and write operation, because imagine two programs are actually trying to read data and then store data. It will corrupt the file and it can make data not persistent or consistent. So it's first lock the file. Then when it's done, it will then check for what type of data it is from here in this construct binary data, because we would want to serialize the node here, the data here, sorry. So we'll check whether it's a text, a number, a boolean, or a null pointer. And since here is a text, what this format here is the H and the exclamation mark is basically that it will tell the struct module, which is the library, the built-in library that we are using to store this data. First of all, serialize the text. Then when doing that, we will then take this, then we will then store the length of the actual byte in a 2 byte format, so that when we're serializing to the disk, we will first take read the first 2 bytes, which is the actual length of the bytes, and then tell the engine to read this many bytes. Or if it's a number, we just store the number in 4 bytes, boolean in 1 byte, or a null pointer in 8 bytes. So when we do that, we will then move to the end. So as I say, in Python, when we are dealing with file objects, there is a marker basically. So we tell that marker to move to the end of the file, and so that we can write bytes at the end. So when we do that, we will then store or write the bytes on this, and then when we're done, we will take the static position from where we wrote the bytes and then return it back into whoever called it, so that when we are retrieving data, we can tell the engine that hey, start from this address, start from this offset from beginning. For example, 18,432. It will jump 18,432 bytes and then start reading from there. Then when we're done with whatever operation that we're doing, we will then unlock it so that we can release the file in case any other program wants to use it. Then we then stamp root address, and the reason that we're doing that is because this binary tree is immutable. So basically, anytime we perform any operation, we don't directly change the data in place. What we do is we copy the data, like we copy the whole binary B-tree data, so that in case if anything happens, for example, let's say your machine shuts down or any error happened, it will roll back to the previous data so that it can preserve the previous data and then keep the data okay. So, and then you may ask again that would it not be tedious trying to copy the whole data? For example, let's say we have 1 million records. You would have to copy the whole data. No, we don't actually do that. What you do is that let's say we change something like 33 and 37. Let's say we put 38 today. What happens is that we first create a new node that points to this node. But now, since this children has changed, the parents will have to change. So we will then copy a new node, copy its data into a new node, and then point it to its parents, and we repeat again, only creating a new node for its parents. Then you ask them, then what will happen to its children and their children? So what we'll do is that the siblings of the altered node points to the altered parent, so that we will not have to copy their own data again since their data was unchanged. And this is what they call structural sharing. That's what they call it, structural sharing. And again, in a B-tree, the number of children that you can have will be equal to the number of keys, or the number of keys a particular B-tree node has plus 1. That will be the number of children it will have. So yeah, and also we will also store the metadata, like the types in the meta block, in that 4096 bytes block. Yeah. Then as we are going to read, like, so that's for writing, but as for reading, we'll go through this metadata block again and read the metadata like text, number, boolean, and then, like I said previously, each B-tree pointer would hold the address of a previous of where their next node is. So we'll then take that address and move the cursor to that address, and then read the appended bytes. Let's say is the appended byte, which is exactly 4 bytes, to know how many bytes to read. Then we read that bytes and then serialize the node. So I mean the serialized node, we will read that serialized node and then deserialize it using a deconstruct binary data, and then we will then return the node to the B-tree. And this is how the B-tree node actually looks like. So here you have a type, which is that is a node text, number, or boolean, which is 1 byte. Then the key count, which will only take 1 byte, and the number of keys, which are whether text or numbers, and n plus 1 byte for the node pointers, which will read 8 bytes. So the reason why this is so, why they are fixed numbers for each particular type of data, is because we don't want to, because I say the engine cannot guess how many bytes to read. So using its metadata to know whether it's a text, number, boolean, or node, we can tell the engine, okay, this is a text, read this many bytes. It's the number, read this many bytes, and like that. Then here, this is how the data is actually stored on disk outside of the metadata, outside of the fixed header. So this is how it will be. So when reading or creating bytes, we would allocate 4 bytes for the length of the serialized data. So anytime it's trying to read or create, it will first take the length of the bytes and then store it in a 4 bytes in a 32 unsigned bit integer and store it there. Yeah, and then this is the address. It's moving. Yeah, so basically all bitry nodes or pages are serialized and appended to the end of the file, and this is how each object on disk will be like. Length of 4 bytes, which is the length of the serialized bytes, because the engine cannot guess how many bytes we should read. But we know that before we try to read any bytes, we will first read the length of the actual bytes from a 32 bits unsigned integer, which is 4 bytes, and it will take it, deserialize it, take the number, like how many bytes we should read, and then read from there. Then we have formats to know what type of bytes we are going to read or store. For example, in a node we have 8 bytes, so it will read 8 bytes, and it has this format so that we can tell the struct module how many bytes we're going to read. And in the root address is stored only in the meta block, because like I said previously, the bit tree is mutable, things cannot change. The bit tree itself cannot change, so we would have to create a new bit tree data structure, and then we write where this new data structure starts at. Then the new versions of nodes are written on updates, yes, immutable and structural sharing. The old nodes also remain on disk. Yeah, and now this may also be a problem, because now that we are appending data to the disk, you may ask that, well, this will take up space on the disk, and this will actually compaction comes in, so that we can then take care of old data. But for me, how I am going to do it is basically I'll just read from the new root address and traverse through the new bit tree data structure, and then write all those bytes into a new file and delete the old file, and then link that new file into the new engine so that it can write bytes there. Yeah, and again, it makes the engine crash safe and simple, so that in case as the engine is writing data to the disk, to the file, it will, as the engine is writing data to the file, and then maybe something happened, maybe your machine went off or something bad happened to it, it will just the new operation may not be successful. Then it will have its old data stored there, so nothing gets erased. Then you can store the previous data that was not successful into there. So again, so I said, why is it called an engine? Because it handles how data is persistent, whether it knows how to serialize or deserialize those, and as well as it also handles file locking, so that no other program can read it, and it also controls concurrency locks. Well, as for my own database, it is actually single threaded, so there is no like multiple operations happening at once together. Everything is serialized up, and everything is linear. Everything only happens one at a time, not in parallel, and it provides primitives for the bit tree to store and retrieve those reliable, and it gives the bit tree to live on. So yeah, basically that's it in a nutshell, and this is actually the actual code. So this is actually code on it. So here, this is the meta block size. So I allocated 4096 bytes. Then the binary formats. These are the binary formats, so that I can tell Struct, okay, how to serialize the bytes. Then this is the binary length to, like, how many bytes to read. Then this is what happens when we initialize the storage. The file object, we would create a file, and the extension does not really matter. Like, let's say we say Mackie.dvd or something like that. It does not really matter because the whole thing is on disk, and your computer does not really care about how it's stored. And again, that extension, like for example Word document, Docs, PowerPoint, and PPTX, is to tell the operating system which program should handle this file by default. Or for me, I don't do that here, so there's no need for that. And again, files are just a range of bytes on disk. So validate meta block. This is just to reserve space for the header. Then lock for process. So what it does is it just locks the file. It just locks the file. So we use portal locker here to lock the file, and it moves to the end. Basically, it just starts from the beginning of when the file starts. Then this is how we store the address, basically using .cell method for file objects in Python. It tells us where the offset is, we store it. Then we perform simple conditional statement where we say if the end address is less than the size, that means that this is the starting of the file, and we then reserve bytes for it. Then we unlock the file. Then we need to validate metadata. So this is where we store the data like text, boolean, depending on how the disk is, depending on how what type of data we're storing. Then we write the binary data to the file and then flush it. And the reason why we do this is because in Python, or I'm not sure about other programming languages or how other programming languages interact with other programs, is basically when we write to a file, Python does not really, does not write the file directly. It first stores it in a buffer in memory, then writes it later. But we don't want that. We want it as soon as possible, so we flush it. Then when we're done, we unlock it. Then if we want to read data, we first jump to where the data is stored, because for the root address we store 4 bytes, like to read how many bytes, like the length of the byte itself, and then we read the other bytes, which is exactly 4 bytes. So that's 4 plus 4, that is 8. So we tell the engine to jump to offset 8, so that I can read the binary length of how many how many bytes are here. You read it, and then we can then retrieve the types of data that is stored there. Then this is when we want to read from disk. So we basically retrieve the metadata. Then we seek the address from the node address that is stored in the node pointer. Then we read, like I said, the length of the bytes from the 4-byte integer. Then we read how many bytes we need to get from it. How many bytes we need to get from it. Then we deconstruct. I'll take the data back. Then this is to store the data back. Yeah, so that's how it is. Yeah, so thanks for the video. Thank you, and if you want to support my channel, and please like and subscribe and tell other people about the video. Maybe it could help them. Yeah, so thank you, and God bless.